It's first of all, it's great to be here, even if only mentally. So been a while since my last marathon, and unfortunately, I'm joining only today. So I'm hoping you all are having a blast since Monday. But what I'll be talking about is multilinguality in transformers and in machine translation. And well, more broadly, I'll start by talking about multitasking and continue talking about multilinguality, how it can be achieved and what it entails, and then finish by talking about interlingua and are we there yet? And well, the outline of my talk is multitasking, then multilinguality and interlingua. So I hope you get questions. I welcome any questions if something is unclear or anything. If you're shy, feel free to ask them on Slido. Just choose this code and write the questions there. I don't know if you've done this before on this marathon, but if you feel like writing something down. But of course, oral questions are totally fine by me. So anyway, the general setup of machine translation nowadays is the following: that you get an input, like a Spanish sentence, which old timers should know back from statistical NMT times, that this was one of the most famous examples. Maria no daba una bofetada a la bruja verde, and this should translate into Mary did not slap the green witch. I haven't seen it used much since neural NMT took over, but oh well. So the whole point, or the general scheme of neural encoder decoder machine translation is that we take the input text, we feed it into the encoder, then the encoder, nowadays with the transformers, produces some kind of a contextual representation for each word. So it started off with one vector for a sentence, but then soon enough with attention, it took over and went ahead and started computing contextual representations for each word separately. So as the output of the encoder, we have the list of vectors or contextual embeddings for each input token. And this is a big matrix, which is, let's say, vertically, it's the size of the sentence when tokenized by sentence piece or some byte pair encoding, and horizontally, it's the size of the embeddings. So easily 512 or 768 or 1024, whatever. And so after this first step, these vectors are fed into the decoder, and the decoder does the encoder to decoder attention and the self attention inside the decoder, and also does either greedy or sampling or this autoregressive kind of generation. And we're hoping for it to turn those contextual embeddings, the encoder's output vectors, into the output, which in this case, in a perfect scenario, should be Mary did not slap the green witch. However, nothing about the methodology used here is specific to machine translation only. So we have a transformer as the encoder with all the self-attention and so on. And then we have the transformer as the decoder with the encoder to decoder cross attention and the self-attention and all the one after another continuous generation. So it's not really specific to translating. Just like the same encoders, but without the decoder, are used as BERT or XLMR, Roberta, BART, and all the other famous models. So we can actually, in theory, we can train it to encode some kind of a sequence. We are in NLP, so let's say a sequence of words, and then produce some other sequence. So the encoder-decoder thing more generally solves sequence-to-sequence problems, and that doesn't have to be machine translation. So as long as we trained it with the right material, it can turn any sequence into a matrix of vectors and then turn those vectors into the output list. For example, we can feed it with English long texts into the encoder and then train it to produce a shorter summary of those texts. Of course, we have to worry about the encoder being powerful enough to encode long texts, and then there arises the whole issue with the usual self-attention having quadratic complexity. So there has been a number of informer, reformer, long former, big bird, and other kind of transformers which optimize this and make attention from quadratic into linear and so on. But the idea stays the same. We can just feed some kind of input sequence here, just a long text, and the model will learn to turn it into something else. In this case, long texts are summarized. Or we can feed it with a complex text if we have enough data, then with supervised, annotated in a supervised way, we give it a complicated text and train it to simplify it. And so all of this is done in the common to machine translation, to neural machine translation, end-to-end fashion. We just give it the input, we just give it the output, and let the transformers figure out what exactly, which kind of representations it needs to compute, and so on. So if we take this idea to the extreme, then, well, actually, Google has done that already. And if we say that it doesn't have to be a single task, we can give it some kind of input which includes the input sentence or text or the input information, and also the code for doing something with that text. So Google in a paper from so Journal of Machine JMLR, it should be not JMRL, so Journal of Machine Learning Research 2020 paper, described the model which they called T5, so text to text transfer transformer. And that was trained with a lot of different tasks, all fed into the same model. These tasks were encoded with text. So it would be trained with things like translate English to German, where the input sentence is "that is good," and that would be trained to translate it as "das ist gut." Or there is this corpus of linguistic acceptability. So COLA is the code for this task of measuring whether the sentence is linguistically acceptable. In other words, is it grammatical or not? So the course is jumping well. It's not about just the grammar. It's generally about whether this is a well-formed sentence morphologically, grammatically, as well as semantically, because the course is jumping well is syntactically a fine, well-formed sentence, but semantically it makes no sense. And so then the output in text is, well, not acceptable. Or another task is, I forget what's STSB, I think, was it sentence similarity or something? There is a long list of these tasks. And so that is trained basically to do regression to predict as text the output 3.8. Or here you see summarization. So the text that is to be summarized is state authorities dispatched emergency crews Tuesday to survey the damage after the an onslaught of severe weather in Mississippi and so on. And that is summarized as 6 people hospitalized after a storm in Atala County. There is a bigger picture for the same T5. There's really a long list of tasks it's trained to solve. There is also the question answering. So below you see a long context. So that's the text based on which the answer is, the question is to be answered. And the question is, what does increased oxygen concentrations in the patient's lungs displace? And the answer should be carbon monoxide. Or there is this premise, water broke, question, what is the effect of that, and whether we should pick he flew to Moscow as a result, or the baby ate chocolates. Here, strangely enough, the correct output is choice 2, even though this is a very long logical connection from somebody's water breaking and the baby being born and growing up old enough to eat chocolates. But if we look at the first example, where her water broke and the effect of that should be a baby girl was delivered, not the baby was entangled in the umbilical cord. So that's not a result of that. So this is another task here. And I have a link to all the tasks included in T5 here. So basically, this was done to summarize that transformers, and especially sequence-to-sequence transformers, so transformer encoders coupled with transformer decoders, can be trained to solve a wide variety of tasks. And it doesn't need to be a single task. It can be a plenty of tasks mixed all into the same model. So if we, for example, for a second here, look at how big of a model do we need? So it makes sense that the more information the model is supposed to learn, the more the more tasks we have, the more text, the more difficult it is to perform the tasks, the bigger model we probably need. So in the paper, Google experiments with, I think, 4 or 5 different setups of models. It starts with a model they call small model. And this small model is actually the default setup of Marian, Fersig, and other machine translation frameworks, where we have 6 layers in the encoder, 6 layers in the decoder. The number of heads is 8. The dimensionality of each head, and so the model is 512. And so if we multiply this by 8, the feed-forward dimensionality, feed-forward layer dimensionality is 2048. And they go from this model, which in total has about 60 million parameters, up to the huge setup with the number of heads being 128, the number of layers being 24 layers in the encoder and 24 in the decoder. And the dimensionality overall is 1K, 1024. And the feed forward is then this multiplied by, I guess the number of heads here. And no, it should be something else. Am I mixing something up? Maybe. In any case, the dimensionality of the feed forward net is then 56,536, 65,000. So typo 65,536. So in total, 11 billion parameters, and they show, of course, that this performs better. So this is to demonstrate that the model capacity actually makes a huge difference on how well this the resulting trained model will perform at these tasks. Because if we just take a small model and just start stuffing all the original tasks, the more the better into it, then of course it will run out of this capacity at some point. So we need bigger models to handle more tasks or more complicated tasks. So if we can train one and the same transformer model to solve different tasks, then it makes sense to assume that we can pick those tasks, all of those tasks, to be machine translation, except one will be translating German to English, for example. Another one will be translating French to English. And let's say a third one is translating Estonian to English. So let's start with easy multilinguality, where we translate many languages into one language. Typically, if you train this in a single direction fashion, then you will get 3 different systems, and you will have to translate so each language pair with a separate system. But the question is, can we stuff all of that into one and the same transformer, into one and the same system with some kind of a setup? And the answer is, well, we can. Since you saw that T5 didn't, I mean, there are other experiments with combining different modules and different pieces of the model for each task. But here, the simplest multilinguality that has been tested since at least 2, 3, 4 years ago with LSTMs and later with transformers is sharing all of the model's parameters and just saying, let's try to use the same encoder and the same decoder to solve all of the included tasks. Just like T5 uses the same encoder and decoder, here we will use the same encoder for all of the input languages, and obviously the one decoder for producing English. How we do this is actually very simple. Since the model knows that it has to translate into English, then we don't need to change anything. We just combine all of our data all together into one big training data set, where we have German input and English output, we have French input, French output, Estonian input and English output, and it just works like that. So we feed it with examples like ich bin ein Kugelschreiber, and this is to be, the model is trained to translate this into I'm a pen. Don't ask where I came up with this example from, but it's just so. It's just language. So, or voulez-vous manger? That's supposed to be translated into would you like to eat? Or see on väga kurb lugu, which is supposed to be translated into this is a very sad story. the encoder simply learns that it gets some input. We train the sentence piece model, so the byte pair encoding, the tokenizer. We train it also on the mix of all these languages to tokenize the text in whichever language it is. We feed it into the encoder, and we train the encoder to encode it into vectors, and those vectors to be turned into English. So turns out it works. There is a paper which I refer to later by the, I think, massive exploration of multilingual MT or something by Google, which actually says that you can inform the encoder about the language it sees. So this can be easily done by simply beginning the sentence with one first token, which will be German, like DE, or French, FR, or Estonian, ET, which will send a signal to the encoder that this is that language. But actually, there is other research which shows that encoders very easily determine by the tokens used and by their sequence which kind of data they're seeing. So in this case, which kind of language they're looking. So this parameterization might not be needed at all. The beauty of this is that there is no change in the data besides just combining it into one big data set, and there is no change in the architecture of NMT. So you can simply take your favorite framework, whether it's Fairseek, Marian, or whatever else, and simply dump the data into it, and you'll get many-to-one translation. However, of course, it makes a lot of sense to evaluate the models on some kind of a dev or test set to see whether the capacity of your model, the width of the layers and the depth of the model and so on is big enough for you not to lose any performance compared to a single direction system. So if the model is big enough, so deep enough and wide enough and so on, then it's possible to translate all of these languages without losing any or without losing much performance compared to an NMT model specifically trained to do one single direction at a time. So that much about many-to-one translation. Can we now try one-to-many? So here we will have English input always, and then the Russian should be either in Russian. So the output should be either in Russian or Italian or Latvian. So here we actually, when we pass the sentence in, unlike many-to-one translation, where the model doesn't need any additional information, it just encodes the input into some vectors and produces English. Here we actually need to give it some additional info about which language we expect it to produce. So whether it's, in this case, one of those three languages, Russian, Italian, or Latvian. And this information can be passed in two ways, and both require some change to some parts of the model. So let's first look at the very common and first to gain notorious popularity way of doing it. Here, you would give the input sentence like, I need money in English, and you would prepend it, or you would add in the end of it, well, doesn't really matter where, you would add a token which specifies which output language is expected. So this is given together with the input sentence into the encoder. So the encoder sees the input as well as what the output language should be. So we train it. So we take the same architecture. I mean, no change in the architecture, but we simply update the data a little bit. And besides concatenating all the multilingual parallel examples, we supply it with the information like to Russian and I need money. And this is trained to produce, or it's given to Latvian, would you like to eat? And this is trained to produce vai jūs gribat ēst. Or to Italian, I am a rhinoceros, and translated or trained to translate in sono un rinoceronte. There is later research which says that actually if you give this information explicitly into the decoder, then there might be some gains. However, this completely works if the model is, well, if the model capacity is high enough, if the model is strong enough, then it's completely possible for it to learn to translate everything very nicely. Even though with smaller models, or if you don't train it long enough, in practice, you can sometimes see that this model can confuse languages. So it might ignore the input tag in some rare cases, or it might just spuriously switch to producing some other language, either for the whole output sentence or for parts of it. So this is tricky because we are approaching multilingual generation here as a black box problem in an end-to-end fashion. We just say, here's the data, and we really, really hope that the model will learn to do it. We don't have specific control over the model's output language. We just pass it the data and we hope that it learns this behavior. And it actually does in most cases. However, there is a different approach which is preferred by nowadays by many systems nowadays, and this is not using tags to pass it into the encoder, but rather using a specific tag in the decoder. So it is trained. Again, there's no change in training, and there is a small change in the decoding. So it's trained by similar data, except the encoder sees the input language, and in this case it is English, and the decoder sees examples like RU and the Russian output, or LV and the Latvian output, or it and Italian output. And when decoding, we treat this token as a beginning of sentence token, and we don't ask the model to produce this is the way how we pass the information of which language it should be on the output. We simply force the decoder to pick the first token to be the output language that we need. So when doing the first step, instead of giving an arbitrary beginning of sentence token and asking for the first word in the sentence, we give it either Russian or Latvian or Italian, and thus we pass this information of which output language we need directly into the decoder, and then it continues to produce the required or the specified output language. So it's again a simple data update. So when training, you give it almost the same data, except now you put the output language into the output. There is no change in training. You can again train it with your favorite architecture and so on. And there is a small change in decoding. So the framework you're using has to support this small change in the decoding by forcing the beginning of sentence token. Hugging Face implementations support this. I think Fair6 supports this. I would assume Marian supports this in some way. I'd be surprised if it doesn't. Yeah, but this is one thing that has to be changed in the decoding. But so this is that simple so far. Now, we've talked about many-to-one, and we've talked about one-to-many translation. What about many-to-many? So let's imagine we have 4 languages now: English, Russian, Estonian, German, and we want to translate between any 2 languages of those. We want with the same system. So with single direction systems, if we really need all of those directions, then we would need 12 different systems. So for each input language, we have 3 other output languages, and we have 4 languages. So 3 times 4, we have 12 systems. And it might be desirable, if we don't want to run 12 different systems, to stick it all of it into one big system. So this is actually quite easy, because the many-to-one translation can be done as is. So we can just pass any languages into the input, or we can opt for adding the first token of the sentence, specifying what the language is. If we don't want to wait for the encoder to learn to determine the language, if we just want to tell it what the language is and make its job a bit easier. And then we choose whichever tactic we want for parameterizing the output language, whether it's a token in the encoder specifying the output language for the decoder, or it's a forcing beginning of token for beginning of sentence token for the decoder, whichever is preferred, or even both. This massive exploration of multilingual things paper, which I have a link somewhere later, at some point said that they determined that the best idea is to provide the information specifying the source and the target language, both into the encoder as well as directly into the decoder. However, nowadays, the big, spacious and wide and deep models, of course, figure this out with whichever method you give to them, as long as they're big enough, trained long enough, and so on. So this is easy. You just do the same thing as you do with one-to-many. You pass the input language, whatever the language is, so English, German, Estonian, Italian, Japanese, Hebrew, or whatever, and you pick with whether the forcing or beginning of sentence tokens or the parameterization through the encoder for specifying the output language. If we take this idea to the extreme, then there were several papers by Google, and now I think the most like the biggest and the most famous open public MT system with this multilinguality in it is the M2M100. So that was created by Facebook, and this is Facebook's massively multilingual NMT system covering 100 languages. There was a lot of peculiarities about it. One peculiarity was that they took the training data and they included not only other languages to English and English to other languages, like it was done by some other models, but they first of all took all of the language pairs, not including English, and they also did this triangulation in the data. So if there's a sentence in, let's say, the same Estonian translated into English and the same English sentence translated into German, then you can extract the Estonian-German pair and train the system directly with it. If I'm not mistaken, they even did back translation with the same model so that later there would be data. I might be mistaken there. I think they discussed back translation, but not use it. Not sure here. But the point was that they took a huge system. They trained it with 100 languages as input and 100 languages as output. And what they got is, well, this M2M. It is available, so two of those models, the small and the medium one, are available on Hugging Face. So if you, so here's a link to the paper, here is a link to Hugging Face. I think we have time to go look at it. Before that, so here's a scheme I took from their paper where the English-centric multilingual system is depicted on the left under A, where the language pairs included in the training include either English and target language or source language and English. And here they included many-to-many multilingual data, and this is grouped into, well, language groups, some families, or some similarity groups between languages, and they included all of that into the training. Furthermore, if we look at their architecture, then they give the information to the encoder specifying the input language. So here's Chinese, which I don't know how to read, and here there is a tag for Chinese. Then the shared encoder produces the vectors. These go into the shared decoder. I mean, the shared decoder means it's shared between all of the languages, whichever language we're trying to produce. And this gets a separate information of French being the desired output language. And they also experiment with adding language or language group specific parts into the model. So after some layers of the decoder, which are shared between all of the languages, some of the next layers are shared only between the languages of the same group. So here's language group B, which I would assume to be Romance languages, and French falls into there. And then it's trained. This part of the model is only trained when when a Romance language is specified at the output. And then language group A is trained only with these yellow languages, with the unspecified yellow languages, or the red ones are handled by the special part of the decoder in language group C, green ones in language group B. If any of you haven't done this yet, then I say check Hugging Face out, because here all of the models are hosted and you can type example sentences here. The one thing is that the one problem here is it also uses this forced beginning of sentence token to generate the output. And so I cannot do it in this hosted inference API. If I type something, I will type and input some text in the source language. And I think it just samples the output without pre-specifying what it should be. If we, oh, it takes longer. I should have taken not the medium language, but the medium model, but the smaller model maybe. Anyway, if we remember to have a look at it, let's look at it later and let's see into which language it will translate it. But basically, you can import it directly from here and use it in your code. You can then even have the online examples here really running and working for you and so on. So coming back to the model here. So this is M2M, basically taking this multilinguality multiple, so many, too many, and training one huge model with diverse parts of the model here vivisected in different ways to handle different languages, or I think they experiment with skipping this part as well to basically translate anything into anything. Here, again, model capacity becomes an important enough issue. And of course, they have smaller versions, but the big version, not the one I'm testing there, the one that's running on Hugging Face in the background in another tab is, I think, 1.2 billion parameters. The biggest one they report is a bit depressing because it has up to 4,096 as the model dimensionality and up to 16,384 for the feed-forward dimensionality, up to 16 heads, up to 48 layers in the encoder and the decoder, which results in up to 12 billion parameters. And this biggest model took them 33 days, as they report in the paper, to train on 512 GPUs. So this is the depressing part because, well, nice experiment, but there is little chance to replicate it unless your Facebook, Google, Hugging Face, Alan AI, or any of the big players. So this is incredibly expensive. But there are smaller models that you can use and you can train or retrain and so on. And thankfully, this and the other models are shared openly, so you can at least fine tune it much faster to a specific language pair of your choice, or a domain of your choice, or some subtask of your choice, much faster than this training from scratch. So there are other models, of course, and there's, for example, the same Facebook's multilingually but not cross-lingually pre-trained NMT. So they describe MBART, which is pre-trained with noisy text denoising. So they add noise to English text and feed noisy English as input and denoised, so correct English as output, and then noisy Chinese as input and non-noisy Chinese as output, and so on. This is pre-trained and then further trained on parallel, so cross-lingual examples for translation, so MBART 50 for translating. And then there's Google's T5, which was, so T5 is only English, and that was turned into multilingual T5. It's not NMT, so they don't translate for all of the languages with MT5 without fine-tuning, but this is a multilingual model trained also on 100-something languages to do the same different tasks for all of these languages. Finally, an interesting link is also Hugging Face, but stuff done by Jörg Tiedemann and his group in Helsinki. Here, if you go here, and we can go here for a second, check it out. So they have 1,340 different models, most of which are bilingual, but some of which are multilingual in one direction, like many-to-one, one-to-many, or several. For example, if we search for Romance languages, there's a system trained to translate one language, English, into all the Romance languages. So French, Italian, Spanish, Romanian, and I think a long list of others. Or here's English into Celtic languages. If we look further, then we can see Romance to English. There is even a multilingual North EU to North EU. And well, how well they work. So here are a couple of links. Massively multilingual NMT in the wild, and massively multilingual NMT general, and an analysis of massively multilingual NMT for low resource languages and so on. Here, the outtake would be, so sometime before when this began, let's say about 2 years ago, where the models were smaller and the grass was greener and the trees were taller, the general conclusion, let's say some 2 years ago, was that doing this massive multilinguality, or doing multilinguality in general, makes sense if you care more about the low resource languages, because these, through this cross-lingual transfer in the shared model parameter, in the shared model parts, the low resource languages gain in translation quality. So if we take some, let's say the same Estonian, which has less data, and this is trained together with Finnish, which is closely related and has more data, then Estonian would probably gain performance and be translated better. However, high resource languages, since the model doesn't, compared to a single direction model for high resource language translation, the model doesn't focus anymore on this high resource language explicitly, then it might lose a bit in translation quality. So this was a conclusion before, that the low resource languages gain and the high resource languages lose some. Nowadays, if you take a big enough, ridiculously large model, and if you train it long enough on a big enough number of GPUs, then actually there is no significant or no loss in translation quality if you do it for long enough. So nowadays, this is done just nicely directly with the right training parameterization or so on. You can actually achieve a big multilingual model like M2M, which will not lose that much. Still, this again is a trade-off between the model performance and the capacity. So to achieve that, you need a model of a huge capacity. If you need a realistic model, let's say for practical purposes, translating a particular domain, particular language pair, and so on, then it's easiest, of course, to take a smaller model and simply find, let's say, pre-train it multilingually or on a general language pair, and then fine-tune it to a domain, so that it just focuses on that domain, and that's it. Now, so far I've been talking about using the same architecture, mostly shared encoder, shared decoder between all of the input and output languages. However, you saw with the Facebook M2M model that some parts of it were put separately and used specifically for a particular language groups. There is a paper from EMNLP 2020 where the authors experimented with a modularized architecture. So they compare, so they focus on multilingual translation, many languages to many languages. They compare single direction systems, so English to Spanish, English to Korean, Korean to English, Korean to Spanish, and so on and so on and so on, to the second version, which is this, what I've been so far talking about, this shared encoder decoder or universal system, where you have one big encoder, one big decoder here, and this is parameterized, or this gets the additional info of which output language it's supposed to produce, English, Spanish, or Korean in this case. Or they do modularized architecture. They didn't actually, so the idea is not did not originate from this paper. There is a previous paper by Firat et al. 2016, if I'm not mistaken, which does a similar thing with LSTMs on a smaller scale and so on. The idea behind modularized architecture is that we will take a usual transformer encoder here, and we will always train it to encode English into the encoder vectors. We will take a separate encoder, so initialize separately and completely, so non-shared separate part of the model, which will be Spanish specific, and then another one is specific to Korean. Then we will do the same with the output. So there is a English specific decoder, there is a Spanish specific decoder, and there is Korean specific decoder. And we will train all of them in a mixed scenario, where every time we see examples for English to Spanish, then the English encoder and the Spanish decoder is trained. Then we continue by including some Korean to Spanish examples, for example, then the Korean encoder and the Spanish decoder is picked. Or then we pass on to data for English to Korean, then the English encoder and the Korean decoder is picked. And all of that is trained all together. So the models don't specifically share any parameters directly. I mean, there are separate encoders and separate decoders. However, they are coupled together in this training scenario so that the encoders always, so all encoders mostly feed sometimes feed into the same decoder, like English feeds into Spanish and Korean feeds into Spanish, or Spanish feeds into English and Korean feeds into English. So that way, the model, the whole mix of all of that, learns to synchronize their representations and to basically to not require any kind of further parameterization. So we don't tell the decoder what the input language was. We don't tell the encoder what the output language will be. It's just a transformer encoder, just encoding its own language. So they, these guys, they test this scenario. They show that this beats universal encoders or shared encoder-decoder approach in the cases that they tested. And this is not a toy scenario. They actually, so the paper is called Revisiting Modularized Multilingual Neural Machine Translation to Meet Industrial Demands. So they tested on a realistic use case with lots of data and so on. And they show that this modularized thing mostly, or in all cases, beats the shared approach, depending on the capacity, of course. And furthermore, it either stays on the same level or even slightly surpasses the single direction systems. So the benefit of modularized thing is that the English encoder is trained with much more English data than in the single direction case. So the English single direction system for English to Spanish only sees the English from the English-Spanish parallel data. And English-Korean sees the English from English-Korean parallel data. Whereas this modularized thing sees English in the encoder, as well as, so when it sees English-Spanish as well as English-Korean data, or we decode into English with Spanish to English as well as Korean English, and so it just sees more data there. It doesn't have this confusing of languages like the universal shared thing does, because basically each encoder has only seen its own language. It doesn't have this universal encoding of all the languages, but then again, it just clearly separates everything into separate parts of the model and encodes everything as is. Now, so far, I've talked about how translation is supposed to perform with the supervised scenario of things we've shown the model and so on. One very interesting effect of multilingual translation was discovered, so by now already 4 years ago. Wow, time flies. Published in the paper, Google's multilingual NMT system enabling zero-shot translation, published in Transactions of ACL 2017. So the point there, and they did not do Estonian, Latvian, Russian, or English here, but the point there was that you can train this one system. I think they did English to Portuguese and Spanish to English, was it, or some other way? I have an analogical example on the board here. So you can train a multilingual system with passing the output language as an input token to the encoder by showing it only English to Estonian data. So you see the gray line going from English to Estonian in this system. We can also show the other language pair here. So we can show Latvian, Russian parallel data to the system. So this multilingual system here, imagine that it has only learned to translate English into Estonian as well as Latvian into Russian. The zero-shot effect is that after learning English to Estonian and Latvian to Russian translation, the model actually manages to translate from English into Russian as well as from Latvian into Estonian. So without having seen any parallel examples for English to Russian or Latvian to Estonian, the model actually manages to translate with, between those. How does it manage to do it? Well, the encoder, the shared encoder, learned to encode English into the vectors, into the contextual representation of this model. And then the decoder learned to take those vectors and to produce Estonian or Russian. So even though the system hasn't seen direct examples for English to Russian or Latvian to Estonian, it learned to encode English or Latvian, and it learned to produce Estonian or Russian. So this can actually work in this cross-lingual zero-shot way without having seen any kind of examples. If we go back to the modularized paper, then they show that this effect is even stronger in their case. So they not only did they test this zero-shot by let's say not including any parallel data, but they also show that you can take an available trained model. In this case, you see it's English, Spanish, and Korean. You can freeze all of the parameters, so stop changing them when the English, Spanish, Korean multilingual system is already trained. And then you can add Japanese to English data and English to Japanese data and train a Japanese encoder and a Japanese decoder in addition to the 3+3 we already have. So we don't, so these authors, they didn't add any Japanese to Spanish, they didn't add any Japanese to Korean, it's only Japanese to English and English to Japanese, so that the Japanese encoder and decoder learn to produce the same kind of contextual embeddings that are expected by the decoders to fit into this shared space of encoder vectors, or what they call is the interlingual space. And so after having learned, after converging this Japanese to English or English to Japanese translation, they actually test and see that the model can translate Japanese to Korean or Spanish to Japanese or so on. Again, without having seen a single example of Spanish Japanese or Japanese Spanish, Japanese Korean or so on in a purely zero-shot manner. And in this case, with separate parameters of the model, so not shared encoders which have seen the languages, but actually separately trained encoders and decoders which just learn to produce vectors from the same space. An interesting effect of that, a side effect of that, is what if we take a multilingual system with many to many languages, and what if we ask it to translate German into German? The result of this, we're slightly running out of time soon. So the result of this actually is that this model, I mean, it doesn't learn to copy German into German. We didn't show it in any monolingual examples. We just showed it German to English, English to German, German to Spanish, Spanish to Korean, Japanese, and others, and so on. And it learns to read in the German part, and it learns to produce some kind of an output, which in this case was asked to be a German part. And we can see it in practice. If we go to this Helsinki NLP model, so you see North EU, so it includes German. Here, this system was trained with a prepending token, so we write the input as the output should be in German. We write some ungrammatical German input. Let's say, ich nehme Buch von der Tisch. So I take a book from the table with completely broken articles and no morphology, no correct forms or whatever. This loads faster than M2M, I hope. And let's see if it copes with the task. Any minute now. Ich nehme Buch vom Tisch. Okay, it fixed the verb, ich nehme, but it didn't fix anything with the book or the table. So let's see if we add the wrong article here. Okay, so now it fixed everything. So if I write something wrongly, ich nehme die Buch vom Tisch, then it fixed that into correct German, ich nehme das Buch vom Tisch. So this is zero-shot monolingual translation because it hasn't seen any grammar fixing examples. It hasn't seen any German to German examples. It simply has learned to read in German, to not pay attention at the exact form of it, but just to encode it into vectors. And it also learned to produce the correct German as output. So let's continue here. As I just described, why this happens, it learns to encode German in, it learns to generate correct German and doesn't learn copying, because if we show it German to German, then it will simply learn to copy the input into the output and probably will copy the mistakes as well. Since it didn't learn copying, it does this in a zero-shot manner and copes with the task. Well, at least partially, as you saw. So if we now move on to the interlingual part, so as a final topic, there is a plenty of multilingual transformers now out there. There is the encoder-only transformers like BERT, so multilingual BERT, XLM Roberta, so cross-lingual models by Facebook Roberta. There's several others. There's also the encoder-decoder stuff like M2M, MT5, MBART, and so on. So since those models have seen dozens or even up to 100 or over 100 of languages, how do they learn to represent all of those languages? So do they, I mean, the model is definitely smart enough to determine early on in the training process which language it's dealing with. So does it learn separate subspaces for the contextual embeddings for each language, or does it really find one universal representation for all of it? One premise for this interlingual thing is, there is work by Facebook guys from a couple of years ago on unsupervised alignment of embedding spaces, even though that was begun with fixed embeddings. So the fixed embeddings like word2vec or fasttext, or the input fixed embeddings of the encoder, they showed that you can actually take the embedding space, which is shaped in a particular way. Here you see X for English and Y for Italian. So cat, feline, car, and deep should in the end become gatto and felino and tauto and profondo. And they devised a method of rotating or transforming one space into another, so that without using a dictionary, we actually get closed vectors like gatto and cat and so on. So this shows that these spaces learned independently are actually quite universal between the languages. And of course, the question is, how universal are they? Do they depend on the language choice? And most importantly, does this also hold for contextual representations? There is a paper which tried to kill this idea overall, which is titled "BERT is not an interlingua and the choice of tokenization," or how was it? They took multilingual BERT. They used the beginning CLS token as the sentence vector, and they showed that in different layers of BERT, the similarity between those sentence vectors for English and other languages, so English Arabic, English Bulgarian, English Czech, English Danish, English Azerbaijani, drops down the further deep into the model we go. So the beginning layers have CLS tokens similar between languages here, like layer 1, 2, and so on. While as the deeper we go, the further it falls, showing that the CLS tokens have separate spaces for different languages and don't actually align, they are not that similar to each other. The point is that they use the CLS token as sentence vectors, and they use a different, so a particular metric for the similarity of those, which was PWCCA. There is a follow-up paper this year, and I'm shamelessly advertising myself because I'm a co-author, where by changing the sentence representation and by exploring different other metrics, actually you can see that the representations by the model's different vectors actually reach very similar representations between different languages. So here again, it's the same, those are the same pairs: English Czech, English Danish, English Bulgarian, and so on. And here somewhere in the second third of the model, around the 8th layer, there is the highest point of embed where the representations are similar. So showing that if you take the word vector mean or average as a sentence vector, then actually those reside close to each other, and so some kind of a language independent representation does exist. Furthermore, this behavior occurs in different models. So not just the multilingual BERT, but also the distilled mbert, cased, uncased, and small and big XLMR. And with the smaller one here, MLM, as well as the bigger one. So this behavior more or less is repeated over all ones, showing that there is some interlingual behavior in there. So in parallel with that, so since those models learn on different languages, there were some attempts. Here are 3 links to papers showing that if you devise your model such that you have an encoder, plus you have a special interlingual part of the model, learning to produce language independent and language universal representations in between there, and then to generate output, then you can actually do it. Then there was a follow-up to that, or was it an earlier system where instead of a separate part of the model, you would actually stimulate the model to learn aligned multilingual representations within the encoder and decoder as is. So here you would have encoders for English and German, and also they did it multimodally, so encoding images as well as speech and so on, and forcing the model to align the representations. Finally, if we go back to the modularized paper, then their conclusion is that even without forcing the model to learn similar representation for the same languages and so on, even without any kind of separate parameters for it, it learns interlingual-like representations anyway. Because the modular encoders synchronize by learning with overlapping decoders, so the decoders expect this similar kind of input from different encoders, and they just learn to produce universal outputs. How universal it is? Well, there is at least 2 papers looking at the nature of this interlingual space encoding. So there's a paper that's on the language neutrality of pre-trained multilingual representations, showing that if you take language centroids, then you can easily see that Turkic languages are close together, Slavic languages are close together, Romance, Germanic, Indic, and others are. And even if you don't compute the Euclidean distances, but actually look at CKA distance, which ignores rotation, translation, like moving and so on, by simply looking at the similarity of the space, then even then, like if you cluster this, these spaces by similarity, you get a very similar result. Here you see Latvian and Lithuanian groups. Here you see, let's say, Slavic languages grouped and Romance languages and Germanic languages grouped all together, revealing the interlingual nature of it, but also showing that the more dissimilar languages are, the further they fall apart in these representations. So there is an interlingual behavior in it, but it's not universal, and there is some difference in those representations. So to quickly summarize, why the yellow thing? Funny. First of all, multilinguality on the input side, so encoding many languages, can be done easily enough by just stuffing all of the languages into encoder, as long as you have capacity enough in the model for it. Decoding can be done by either prepending the input with tags or forcing the beginning of sentence token, and then you get different languages on the output. You can of course combine those. And I also told you about modularized architectures. I tried to get you inspired by zero-shot stuff, and we briefly and hurriedly discussed interlingua. So thanks a lot. I'm not sure if, so Jose, I hand it back over to you for questions or anything.
Yeah, thank you. Thank you for your presentation. Super interesting. I actually have a couple of questions, and I think that we have one, but I'm not sure we have much time. So I think Tom's made a question. Are you aware of any significant shortcomings of multilingual MT? Or is this really free lunch that was never promised?
So depending on the approach and depending on your capacity, I mean, so it's mixed. I mean, let's say 2 years ago, it was clear that big languages will lose and small languages will win if you do it multilingually. Nowadays, I mean, if it's a big enough model, then I guess you don't lose much, but then you lose money you paid for the GPUs. So whether you can call that a free lunch or not, I'm not sure. I mean, it's quite an expensive free lunch, but yeah, in the end, it seems that if you train it long enough, make the model big enough, then you can get it performing nicely for all of the languages involved. And of course, zero-shot stuff will never perform as well as it would perform if you actually show the model at least some examples of the language pair and so on. So it's not as magical as it is like that. But I don't know. I hope that answers it.
Yes. Okay. I think in interest of time, we pass now for the next session. Amin is chairing it. And please make your questions and talk to Mark on Slack. I think there is a channel just for this talk. I'll make sure I'll make some questions there actually. So thank you, Mark. Amin, on to you.
Yeah, thank you very much, Mark, for the very interesting presentation. I think